Hello everyone, my name is ZhenHuang and I'm from DePaul University. In today's talk, I'll present our work titled Fine-Grained Program Partitioning for Security, which is a collaborative work between DePaul University and Pennsylvania State University. First, I will briefly present some background on using program partitioning for software security. After that, I will move on to our work on fine-grained program partitioning. Then I will describe the implementation and evaluation of our prototype. Lastly, I will present the conclusion. Software vulnerabilities remain a critical issue for software security. For the last 3 years, over 53,000 vulnerabilities were disclosed. Particularly, a Russian-based espionage campaign compromised several United States federal agencies in 2020 by exploiting vulnerabilities in a number of popular software, such as VMware Workspace. Exploiting vulnerabilities in privileged code posed the most severe damages, because once an attacker compromised some privileged code, the attacker can gain access to privileged data and can inject code that will be executed in the same privilege as the privileged code, so that the injected code can execute privileged operations. One approach to address the exploiting of vulnerabilities in privileged code is to apply the principle of least privilege to the program. Particularly, we can separate a program into a privileged part and a non-privileged part, so that vulnerabilities in the non-privileged code will not interfere with the code and the data in the privileged code partition. The benefits of partitioning a program include: first, each program partition can run in its own address space. Second, the partitions can communicate via a guarded interface, so that the traffic between the partitions can be verified at runtime. Therefore, program partitioning can improve software security. Even when an attacker compromised the program partition running the non-privileged code, the attacker, while having a difficult time to get access to privileged code and privileged data. This significantly raises a bar for the attackers. Many approaches have been proposed to automatically partition a program for the purpose of security. Typically, each program partition is implemented as a separate program. And each partition can communicate with other partitions using the remote procedure call or RPC mechanism. Naturally, this kind of program partition separates a program at the function level, because each RPC call is invoked at a function level. So all the non-privileged functions and data are put into a non-privileged partition, while the privileged functions and data are put into a privileged partition. However, there's an issue with function level partitioning. That is, how do we partition functions containing intertwined privileged code and non-privileged code? For example, the figure on the left shows a function A contains intertwined privileged code and non-privileged code. Where should we put this function A? Should we put it into the non-privileged partition? We can't, because it contains privileged code. Can we put it into the privileged partition? Neither can we, because it contains non-privileged code, which may be executed only in a non-privileged partition. A naive solution is to move or wrap the privileged code into separate functions in the privileged program partition, and change or replace this privileged code in the original function A into RPC function calls into the privileged program partition. As we can see from this figure, the first part of the privileged code is wrapped into a function A1 residing in the privileged program partition. while the second part of the privileged code is wrapped into a function A2 in the privileged partition. And in the original function A, we replace the privileged code with RPC calls to A1 and A2 respectively. This solution can result in a high number of RPC calls between partitions because it puts each separate privileged code into a separate function in the privileged partition. And this will cause high runtime overhead. Next, I will move on to our work on fine-grained program partitioning, which will address the aforementioned issue. Our approach partitions the code within a function because it operates at a granularity smaller than a function. We refer to it as fine-grained program partitioning. Using the previous example of function A, our approach will create a new function A containing only non-privileged code, which will reside in the non-privileged program partition, and creates a new function A star containing only privileged code from the original function A, which will reside in the privileged program partition. Our approach uses static program analysis to partition functions in existing programs. It focuses on two hotspot programming patterns, which refer to the programming patterns with intertwined non-privileged code and privileged code. The approach merges code together in order to reduce the number of RPC calls between partitions. The first pattern refers to the case when non-privileged code is followed by privileged code, as illustrated on the figure. The non-privileged code typically interacts with the user to retrieve some data from the user, and then pass the data to privileged code. Our solution for this pattern is to merge all the privileged code in the original function into a new function in the privileged program partition, and let the original function uses RPC call to pass the data from the non-privileged partition to the privileged partition. The second pattern refers to the case when privileged code is followed by non-privileged code. As illustrated on this figure, the privileged code typically would produce some results which will be checked by the function to determine which part of non-privileged code will be executed. For example, this can be implemented as a switch statement, and different non-privileged code can be separate cases of the switch statement. And once the privileged code produces the result, one of the cases of non-privileged code will be executed based on the value of the result. A more complex case of the second pattern can involve multiple instances of privileged code and non-privileged code, as we show in this figure. Our solution for this pattern is to move all the privileged code from the original function into a new function residing in the privileged partition, and make the privileged function to return a value to indicate which case of non-privileged code should be executed. So the original function will make a RPC call into the privileged partition to execute the privileged code. And based on the result of the RPC call, it determines which case of non-privileged code should it execute. Our approach involves 4 steps for program partitioning. First, it will identify hotspot patterns in a target program by using static program analysis. For each of the hotspots, it will create a primary function A star containing all the privileged code from the original function. Then it will create a secondary function, which is the modified original function, that will make an RPC call into the primary function and determines which case of non-privileged code should be executed based on the return value from the primary function. And lastly, it will produce the RPC interface between the 2 program partitions. For each hotspot. We have implemented a prototype based on this approach, it can partition C and C++ programs. It can automatically identify hotspots, creates primary functions, and creates secondary functions. It performs the static analysis based on LLVM. All the primary and the secondary functions are automatically created in the form of source code. To make it easier for developers to examine the automatically partitioned code, we evaluate the prototype on 10 networking and interactive programs, including SSH, wget, and 8 Linux shadow utilities, such as chsh to change the shell, passwd to change the password, user_add to add a new user, userdl to delete a user. Our prototype effectively partitions all the benchmark programs by automatically identifying hotspots, creating primary functions, and creating secondary functions. The partitioned programs has a mean runtime overhead of 5.2%. By merging the code for each partition, it speeds up the performance by 1.38 times, comparing to the naive approach. To conclude, our fine-grained partitioning enables the separation of intertwined privileged code and non-privileged code within the same functions of target programs. This allows the application of the principle of least privilege onto target programs to reduce its attack surface. Our approach improves the performance of partitioned programs by separating privileged code and non-privileged code within the same function. Thank you, and I'm happy to take questions now.